Hello, everyone, and welcome back. This is Dr. Zach. For Unit 3, we're going to use those basic derivative rules that you practice in Unit 2 in order to solve more complex problems. We're going to start with implicit differentiation today, and then during the next class, we will have related rates problems. So let's get started. So for your lesson preview, you were asked to determine dy dx given this function. Now, our goal for this preview is to really focus on the notation dy dx. When you found the derivative of y, you wrote dy because that's similar to delta y, or change in y, and the dx was telling you you're specifically looking in the x direction for your denominator. So dy dx was very specifically chosen as your notation. You're finding the derivative of y with respect to x. Now, for this particular problem, you certainly used your chain rule and knew your basic derivatives. For question B, the notation is similar. You were asked to find ds dt. So that was the derivative of s with respect to t. And when you found that derivative, once again, you used your chain rule. And since you wanted to know where your velocity was equal to 0, you took your derivative and set it equal to 0. So in this problem, you should have found the velocity is 0 meters per second at 1 over root 6 seconds. But ds dt is the focus of this problem as we leap into our next lesson. So let's use ideas from our lesson preview and discuss explicit and implicit expressions or equations. So as I'm looking at my explicit equations, what I notice is that we have a variable which has been isolated, written as a function of other variables. Similarly, we have s of t written as a function of t. Now, implicitly written equations have x and y on the same side. They're a little bit more challenging to solve for one of the variables. For example, if I try to solve this equation for x, then I would have a square root in my problem, and I would have to consider the domain restrictions of that square root. My volume equation, I could easily solve for h, but r might be a little bit more challenging. So implicitly written equations have your variables a little bit more mingled. Now, for example 1, as you can see, the directions say find the derivative with respect to x. You have not given that much thought, though. What we're actually doing is applying a chain rule for each problem. We know that the derivative of x cubed is 3x squared, but I want you to think of x for a moment as the inside of the function. And then the derivative of the inside would be dx with respect to x, which cancels out and becomes 1. So the derivative is really 3x squared. But you have been completing the chain rule since we began derivatives. Now, as we think about dy dx for this explicit equation, the derivative of y, you are physically taking the derivative of y with respect to x. And then that equals the derivative of x squared, which is 2x to the first power. And that you could write dx as well, which is 1 and does not matter. So the derivative of y with respect to x is 2x. So every time you have been finding the derivative of y, you have been finding it with respect to a different variable. Now, how this comes into play. When I find the derivative of x for the variable x, you get dx, which is 1. But then I'm looking for the derivative of y, and that would be dy dx. So every time you find the derivative of y with respect to x, it is dy dx. And every time you find the derivative with respect to x, for x, it is 1. All right, now let's look at example 2. Now for this one, There are similar problems, as you can see. I'm looking for the derivative of y cubed with respect to x. Follow the chain rule. 3y to the second power, but the derivative of y is dy dx. So really, the derivative of y cubed is 3y squared dy dx. Now, you don't have to write those parentheses. I'm trying to demonstrate the chain rule. Okay, looking at our next problem. Did you notice you have a product rule? So you're going to have to pull out the first times the derivative of the second plus the second times the derivative of the first within this problem. We will call x the first. So, first, the derivative of the second now is going to be 2y. I'm finding the derivative with respect to x. So that'll be dy dx. Plus the second, which is y squared, times the derivative of the first, which is 1. Just going to clean it up a little bit. We have our 2xy dy dx plus y squared. Now, as you look at this problem, I want you to count the number of variables. There are actually 1, 2, 3 different variables in this problem. Those 3 variables are x, y, and dy dx. It's its own separate variable. All right, now with this, you should be asking yourself, if I can find the derivative with respect to x, can I find a derivative with respect to anything? And the answer to that is yes. So the derivative with respect to t would be 3y squared dy dt. And if I were to find the derivative with respect to t of that product, we would come up with, first, derivative of the second, so that's 2y dy dt, plus the second, which is y squared, times the derivative of the first, which becomes dx dt. So it's important to make certain you understand what you're finding the derivative of as you look at each individual piece. Implicit differentiation is going to take a little bit of practice on your part. As we look at the next problem, what I need you to look for is what are we finding the derivative with respect to? And then look for the relationships in the problem. You have multiplication occurring here. Negative 3x is going to be multiplied by the y. So that is a product rule. I'm going to consider negative 3x as the first, and then y will be my second. So let's take the derivative. The derivative of 2x squared is 4x dx dx. Now we have to think about the product rule. We will have the first times the derivative of the second, which will be dy dx, plus the second, which is y, times the derivative of the first, which is negative 3 dx dx, but that is just 1. And so we have the product rule complete. Plus, now the derivative of 4y cubed is 12y squared dy dx. Don't forget that. And that will equal the derivative of 4, which is 0. All right, now this looks messy. So our directions were to find dy dx. As you can see, dy dx is occurring in 2 parts of the problem. So we're going to keep negative 3x dy dx and positive 12y squared dy dx on the left side, and move through subtraction our negative 3x to the right, make it negative 3y, make it positive 3y, and then we will subtract 4x. After that, we're going to factor out dy dx. Get those algebra skills in place. You have your negative 3x plus 12y squared equals your 3y minus 4x. Do a little division. Dy dx is equal to your 3y minus 4x over negative 3x plus 12y squared. There we go. Now, the next part of the question says determine dy dt. That's incorrect. We're going to find dy dx at 0, 1. So, just like every ordered pair, x is 0, y is 1. Do your substitution. Dy dx is going to be equal to 3 over 12, which is your 1 over 4. So let's take a look at example 4. We first want to know, where does dy dx equal negative 3? So before we can figure that out, let's find the derivative. We get 2x plus 6y dy dx equals 5. No, wait, that's a rookie error. I knew you would catch that. It's not 5. The derivative of 5 is 0. So that's a very common error. Keep an eye out for that. We're told that dy dx is negative 3. So I'm going to fill negative 3 in for dy dx. We get 2x plus 6y times negative 3 is 0. Or we know that 2x equals 18y. Do a little division. X is 9y. All right, so we know that when dy dx equals negative 3, x is 9y. We can do better. We're going to substitute now. If we go to our original equation and substitute 9y in for x, we're going to get 81y squared plus our 3y squared equals 5, which leads us to y squared equals 5 over 84. And then, of course, we can find a nice little square root. We have two answers. Y is plus and minus the square root of 5 over 84. So that's not a very elegant answer, but that is what we have. But if that's your x value, y value, we now need to find x, which leads us with x equals 9 times the square root of 5 over 81, when y equals the square root of 5 over 84, sorry, that's a 4, and x equals 9 times the negative square root 5 over 84, when y equals negative 5 over 84 with your square root. Okay, guys, so you now know the 2 points where this equation has a slope of negative 3. So as you think about implicit differentiation, make certain that you differentiate both sides with respect to whichever variable you're told. Then if you want to collect all your dy dx's so that you get them all on one side, that'll work. Factor out dy dx and solve for dy dx. You have 2 questions that I want you to try. I do want you to be aware, for question 2, you have 2 product rules to consider. So give these problems a try, and then check your answers. Okay, so what we're going to do next is find the derivative of a trig function. And as we do this, let's look through the cosecant. You know we're going to keep the cosecant y, cotangent y, but now we need the derivative of y. Using implicit differentiation, we get dy dx, and that will equal the derivative of x, which is 1. Now if I solve for dy dx, I get 1 over negative cosecant y, cotangent y, and you guys are awesome algebra students. You would never, ever leave a trig function as 1 over cosecant cotangent. You would rewrite this as negative sine of y and then tangent of y. All right, so this would be negative sine y, negative cotangent y. Now, all right, so now if we were to look at number 6, example 6, determine the equation of the tangent line at the given point. You can see that we have quite a complex problem here. What we're going to do is a product rule or algebra. Now hold on. Let's do a little bit of algebra with this. That 1/5 power is really bothering me. What if I were to write y equals x times 3x cubed plus 2x to the 1/5 and raised everything to the 5th power? What would happen? I would get a y to the 5th equals x to the 5th times my 3x to the 3rd plus 2x. Well, that's nice. And then maybe I'll do a little bit of multiplication. That gives me 3x to the 8th plus 2x to the 6th. So this might be a little bit easier to find your derivative. So let's see here. We need dy dx in order to write the equation of the tangent line, because dy dx is your slope. That gives us 5y to the 4th dy dx equals 24 x to the 7th plus 12 x to the 5th. Now, we're told specifically to find the slope at 2, 4. So I'm going to figure out my substitutions. I get 5 times 4 to the 4th dy dx equals your 24 times 2 to the 7th plus 12 times 2 to the 5th. And when you solve for dy dx, you're going to come up with a 27 over 10. All right, now once you have your dy dx, you can finish the problem. You get y minus 4 equals your 27 over 10 times x minus 2, and then you are all set. Now, as I already told you, implicit differentiation is going to take some practice. So right now, I have a series of questions that I would like you to work on, and we're just going to pick some of them. You don't have to do all of them right now. Questions numbers 4, 6, 8, 10, 14, 16, 24, 26, 28, and 30 ought to do it. So give these a try, see how they work out, and we will chat in a few minutes. So for this lesson's homework, make certain you practice implicit differentiation, check your answers with CalcChat, and make certain you give the rock problem a try as part of your homework assignment. Have an excellent day.